working? Is that a yes? Yeah, good, good. Right, so yes, that is what I'm going to be telling you about today. Basically this is a summary of the sorts of things that, here we go, of the sorts of things that we're going to be talking about today. You've already been introduced to neutrons and the properties of the neutrons. I'm going to go over this very briefly, and then talk about elementary excitations in solids, primarily phonons and magnetic excitations, and essentially how we might study them with inelastic neutron scattering and why we might be interested in doing that. Then I'll talk in some detail about two different types of inelastic scattering instruments, which are widely used, triple axis instruments. So these are the instruments that were first developed by Burt Brockhaus, and that's why he won the Nobel Prize. And then chopper techniques, which are the sorts of things that you see here, and the sorts of instruments that kind of lead up the inelastic area here at the SNS. And then I'll finish off with some practical concerns. So this lecture is actually 2 lectures, so it'll go on for the better part of 2 hours. And you may have noticed, if you've looked ahead, there's a lot of slides. And actually, there's more slides than I think we can get through, so we'll just go as far as we can. Feel free to interrupt with questions at any point. And I'm not too worried about whether we get through everything or not. And some of the items that we've got, that I've got in the notes, have actually been covered or will be covered by other people, so I'm going to go through them rather quickly. Let's see. So you've already heard about the properties of the neutron, and I don't know if you've been to HIFER yet. Have you been to HIFER yet? Yeah. So have you seen the reactor at HIFER yet? Have you seen the blue glow? You haven't seen the blue glow. Okay. Well, it is possible to see the blue glow. So this is actually a picture, quite an old picture actually, but you could take the same picture this morning if you wanted to, of the McMaster nuclear reactor. So McMaster has a small nuclear reactor, 3 megawatt nuclear reactor on campus, and it is used for some neutron scattering applications. But one of the things that's quite impressive about it is that it's basically a swimming pool, and you can stand essentially on top of the swimming pool and look down on the core of the reactor, and that's what you see here, as it's operating. And what you see, if you look down there, is you see the core itself. So the core itself is this cube that you would see here, and it's a cube that's made out of material that contains uranium. Okay, it's fissile material. The cube, you could, in principle, you could well, I wouldn't say you could hold it, but you could get your arms around it. Okay, it's about this big, and so it's not even all that big. It's made up of an assembly of material which contains uranium, and the reaction that keeps it going, which you already heard about, is it's uranium-235. That's a fissile isotope of uranium, absorbs a slow-moving neutron, breaks up into 2 smaller nuclei, and gives out 2 or 3 neutrons in the process and some gamma rays. And so what you're seeing, the blue glow that you're seeing, is the result of the gamma rays primarily, and also the daughter nuclei. They're ionizing the water molecules, the H2O molecules, and producing electrons, which are very energetic, because this nuclear physics process is very energetic. And the net result is that you get very energetic electrons propagating in water. And they're, in fact, propagating faster than the speed of light in water. And that produces this Cherenkov radiation, this blue glow. Okay? So actually, this process, you can sort of see that you've got 1 neutron in and 2 or 3 neutrons out. So if you run this forward a few generations, you'll get a lot of neutrons. Okay? And so, we've got this. So this blue glow is not the neutrons, but you can think of it as sort of a cloud of neutrons, a gas of neutrons that's being produced, and then we've poked holes in the side to let some of the neutrons come out, and that we're going to use for our experiments. Okay. And of course, the neutron, the characteristics of it that we're interested in, it's got no charge, so it doesn't interact directly with the electrons in solids. And for the most part, as materials physicists, chemists, and materials scientists, we're mostly interested in electrons in solids, and neutrons don't interact with electrons in solids directly. Okay, so that sounds like it's not a great starting point. But they do have a spin-a-half magnetic moment, so they can interact with magnetism in solids. So that's how they interact with the electrons in solids. It's through their magnetism. And they have mass, okay? So the fact that they have mass, means that higher energy neutrons are going faster, lower energy neutrons are going slower. Okay, that may seem kind of obvious and a detail, but that's not true for electromagnetic radiation. Electromagnetic radiation, photons, X-rays, doesn't matter what their energy, they all move at the speed of light. Okay, so you can't time them and get some information out of them. So this you've seen before. These are the two ways that we generate neutrons. So the first one is what I was just talking about. This is fission. Here's our uranium-235 nucleus. It absorbs a slow-moving neutron, breaks up, and produces about 3 neutrons in the process. So as I say, if you run this reaction forward, you get a very high density of neutrons in a gas that you can then access. So spallation is somewhat different. We've got protons that come in with a certain time structure. So they come in here at the SNS every 60th of a second, and we run them into a heavy metal target. Again, here it's mercury. And that destabilizes the mercury nucleus, and it boils off a whole bunch of neutrons, and protons actually, but mostly neutrons. And we use this burst of neutrons and its time structure to do neutron scattering experiments in which we take advantage of the fact that the neutron is a massive particle, and so we can time it. So this just shows schematically how this works at the SNS. I know you've seen this before. So for a spallation source, it's really a proton accelerator that's at the front end that's going to produce a current of protons, current of protons, which start off with a time width of about 1 millisecond, but when they go into this accumulator ring, they come out with a time structure of about 1 microsecond, and then every 60th of a second, this pulse of protons gets delivered to the target, and you get a burst of neutrons every 60th of a second. Okay? And that's what we're going to end up doing our time-of-flight neutron scattering experiments with. So this is just a summary of all of that. The neutron has a certain mass. Okay? It's not very big, but the fact is it's not zero. Okay? That's all we really care about. No charge. It's got a magnetic moment. So the neutron does not interact directly with the electrons except through their magnetism. So the way it interacts with atoms, if it's not going to be through magnetism, is through nuclear interaction. So the neutron itself is a nucleon, right? And it's going to interact with the nuclei in atoms. The nuclei in atoms are made up of protons and neutrons. So the neutron's going to have a hardcore interaction with the nucleus, and so it's going to essentially have some sort of billiard ball type interaction with the nucleus, and that's how it's going to sense that the atoms are there if it doesn't do so via the magnetic interaction. So one of the things that means is that the neutron is going to be sensitive to different types of atoms, but more properly or more specifically, it's going to be sensitive to different types of isotopes of the atoms, because the neutron is interacting with the nucleus. So if the nucleus is different, the neutron sees it as different. So the neutron sees hydrogen differently than deuterium because the nucleus in hydrogen and deuterium are different. Okay. So so the neutrons interact with the nucleus, and so we can then use that interaction to do diffraction and understand crystal structure, and also the normal modes of the crystal structure. And the normal modes of the crystal structure are the phonons. Okay, so the atoms in your in the crystals that you're interested in, they're not statically sitting at the equilibrium positions that we might sort of visualize them to be at. Okay, they're in motion, And it's only their time average behavior which puts the atoms at that particular point. Okay, and they have normal modes of vibration, and we can understand those normal modes of vibration by doing inelastic scattering experiments. That's what we're going to be talking about. Okay, and all that, so that's the sort of thing that that would be the outcome of our neutron experiment, is to understand these normal modes of vibration. Okay, so that's this type of interaction where the neutron comes in and scatters off the nucleus. The neutron also has a magnetic moment, and it can scatter off unpaired or uncompensated magnetic moments in a magnetic solid. So if there's a magnetic solid with atoms that have, say, a single unpaired electron, the neutron's dipole magnetic moment can scatter off the dipole magnetic moment of a magnetic atom. Okay? And so in the same way that we understand crystal structure and the normal modes of the crystal, we can understand magnetic structure and the normal modes of the magnetic crystal, which are the spin excitations, spin wave excitations, and whatever the spin excitations are. Okay? So actually, I'm going to have the third lecture that I give, or the third hour, will be devoted entirely to this. So I'm going to kind of go pretty quickly through it this first time. Okay, so the neutron, of course, is a wave. I mean, in quantum physics, everything is a wave. So it's not very surprising that the neutron is a wave. And it has a particular neutron de Broglie wavelength. And this is a good thing because it means that we can do meaningful diffraction experiments, meaningful constructive and destructive interference experiments. So the neutron has some de Broglie wavelength, which is determined essentially by its mass and its velocity, and correspondingly it has some wave vector k, which is just 2 pi over the wavelength, and a characteristic energy which goes inversely as the square of the neutron de Broglie wavelength. Okay, so this is actually not too hard a relationship to remember. It's the energy in millielectron volts is 81.8 divided by the wavelength squared in angstroms. Okay, and a characteristic temperature associated with a neutron is given by just, if you were to invert this, you would have a neutron with 1 millielectron volt energy corresponds to a temperature of about 11 Kelvin. So if the neutron transfers 1 millielectron volt in energy to your sample, and that's the sort of thing we're going to be talking about when we're talking about inelastic neutron scattering. We're talking about the neutron scattering off your sample and transferring some energy and some momentum to the sample. Okay? And so if it transfers 1 millielectron volt in energy, that equivalent energy in temperature is about 11 Kelvin. Okay? And that's worthwhile keeping track of. So neutron scatterers, they tend to divide neutron energies up into 3 categories, in part for convenience, but in part because of the way we manipulate the spectrum of neutrons coming from a reactor or coming from a spallation source. We do that with what's referred to as a moderator. And the moderator can shift the energy of neutrons to either energies that are higher than what would naturally come off the source or lower. Okay? And so we talk about neutrons, we talk about cold neutrons, for example, which are basically any neutrons less than about 10 millielectron volts in energy, and these are kind of fuzzy boundaries. Okay? And they would have de Broglie wavelengths between, say, about 4 angstroms and 30 angstroms. So cold neutrons have long wavelengths, and that means that they're very good for determining structures that are relatively large. So macromolecular structures, long wavelength structures. Okay? So cold neutrons go very well together with nanostructure, for example. And if the wavelengths are long, then the energies are short. Or sorry, the energies are small. Okay? And then thermal neutrons, which is what you would typically get off of a reactor-based source if you just have the neutrons come into equilibrium with the water around the reactor, because the water around the reactor is at room temperature. It's 300 Kelvin. So these energies are about 5 to 100 MeV, and the de Broglie wavelengths are typical of interatomic spacings, about 1 to 4 angstroms. So any material that you're interested in, if you look at, what's the near neighbor distance between atoms, it's about 3 angstroms. Okay, it doesn't matter what material you're looking at, that's the near neighbor distance. And so the de Broglie wavelength for thermal neutrons is about 3 angstroms. And this is why neutrons are so good at resolving conventional crystallographic structures, and we use them all the time for that. And then hot neutrons, anything over about 100 MeV, and they have relatively short wavelengths. So that's just some of the nomenclature that goes with this. So then this is the experiment that we do. And basically, this summarizes, it looks kind of simple, but this summarizes every experiment you would ever want to do with a neutron beam, okay? So it's actually a pretty simple business when you get down to it. So the basic experiment is that we've got some incident beam of neutrons. It has some characteristics, which I'm going to come to in a moment. It scatters off the sample, and what we're interested in is understanding the relative intensity of scattered neutrons after it's scattered off in some direction, okay? And so there'd be 2 angles which would define that direction. And we may or may not be interested in the energy distribution of this scattered beam, okay? So that's every experiment we would ever do, okay? And so now the details of the experiment come into the details of the incident beam and the scattered beam, and we basically have 3 choices for the incident beam. Okay, it's really 1 choice, as I'll describe in a moment, but I'll start off saying that it's 3 choices. So for the incident beam, we either have a monochromatic incident beam, so we either have a single energy or a single de Broglie wavelength coming in here and scattering off the sample, or we have a white, what I'm going to call a white incident beam, which means that we just take all energies, every single neutron that's coming off and going in the right direction, going towards our sample. We don't care about which energies are coming out there. They've got a very broad spectrum of energies typically. It's whatever your source is producing, okay? And we're just going to let them all scatter off the sample together, and then we'll worry about what happens afterwards. Okay, that's referred to as a white beam. Or we would have a pink beam, okay? And a pink beam is somewhere in between a white beam and a monochromatic beam. And what it means is that you've actually done something to the incident spectrum of the neutron beam such that there's a low energy cutoff and there's a high energy cutoff. And you're taking all the neutrons between some low energy boundary and some high energy boundary, okay? So those are the 3 possibilities for the incident beam. But what I'm going to tell you is that actually all of these are a pink beam. They're all a pink beam. Because even when you think you've got a monochromatic beam, it's not really monochromatic. It really does have a lower energy bound and a higher energy bound. It's just that the low energy bound and the high energy bound are getting quite close together, okay? And so if you were to bring them together absolutely, then you would have a monochromatic beam, but you'd also have no intensity, okay? So you don't actually want a completely monochromatic beam because you wouldn't have any intensity, so you back those off until you've got some intensity to work with. And you might back them off entirely if that suits your purpose. So that's the incident beam. And then the scattered beam, okay, we're going to measure, so I'm going to ask you to imagine that there's a beam of neutrons, coming out of the board in back of me. And because my head is at about the right position, you can imagine that my head is the sample. And so the beam of neutrons is going to impinge on the back of my head, and then it's going to scatter off in all these directions. Okay, and what we're going to be interested in doing, at least in principle in our experiment, is we're going to want to know what's the relative number of neutrons, or what's the relative intensity that scatters up over here compared to there, compared to there, compared to there, all these different directions, okay? And we can define what those directions are. We can say that I want to pick a part of solid angle that's up in the balcony over here, and it has about a 2-degree range horizontally and maybe a 3-degree range vertically, something like that. So some little patch of solid angle. I want to know what's the relative intensity of neutrons going there, compared to there, compared to there, compared to there, and so on, okay? So I want to know the relative fraction of the neutrons that scatter off in all these directions, okay? And, okay, once I've determined that, then I want to know, is there some particular energy dependence? Is there some energy spectrum to the neutrons that are going in that direction, and is it different from the neutrons that are going in this direction, and so forth? So that's the sort of thing that we want to do. So with the scattered beam, we can either no matter what we do, we're going to understand this angular dependence to the scattering experiment, because that's a scattering experiment. But we can either resolve the energy of the scattered beam or not, okay? Or we could filter its energy. And filtering its energy is, again, you take a low energy cutoff and a high energy cutoff, and you just take everything that's in between. Okay? So there. So that, in a nutshell, is every scattering experiment ever performed. Okay? And we're going to try to understand every scattering experiment ever performed. And the way that we're going to do this is through a formalism that physicists refer to as Fermi's golden rule. So actually, how many people have a physics background? Okay, so it's probably about a third to maybe a little bit more than a third. Okay, so if this makes sense to you, that's great. And if it doesn't, don't worry about it, because we're not really going to use it in any detail. But hopefully it makes some sense. So this is simply a way of calculating that relative intensity, that relative fraction of the neutrons that scatters up in a particular direction and with a particular range of energies, okay? And so this is referred to as Fermi's golden rule, and within the first Born approximation, again, if that means anything to you. So this first Born approximation, what that actually means is that the neutron is a weak perturbation to your sample, okay? So the neutron, it's of course changing the state of your sample, but it's doing it in kind of the gentlest way possible, okay? And so neutron scattering, so if you go back several presidential elections ago, there was something about a kinder, gentler approach to politics. It's hard to imagine today, but that's the way things were discussed about 3 or 4 presidential elections ago. So at that time, people started to call neutrons the kinder, gentler probe, because neutrons are a weak perturbation to the probe, and that means that you can use techniques like this, okay? And if you can use techniques like this, one of the consequences is that the neutron scattering cross-section, which describes the neutron scattering experiment, okay, is quantitatively understandable. So the theorists can calculate exactly what you measure, okay? And that's a tremendous advantage, and that's not true for actually for many other probes. Okay, so anyway, what they calculate is this transition rate. And the transition rate is basically, what's the rate at which a neutron gets scattered, from the sample up to a particular element of solid angle with a particular energy range up over here. That's the transition rate. And what it depends on is actually not very much. Okay, there's some factors here that just make it dimensionally correct. There's a matrix element, so this is where, if you like, the real science goes on. So this is a matrix element which describes how the neutron is interacting with the sample in its initial state and converting both the sample and the neutron to their final states, okay? And then it's that quantity squared. We're going to discuss how to calculate that, okay, at least in some approximation. And then we've got what's referred to as a density of final states. So this refers to the final states of the neutron. So this density of final states will give you this term kf that you see over here. So this is the wave vector of the scattered neutron, okay? And actually, we're not really interested in the transition rate that you calculate here. We're interested in the transition rate divided by the incident flux, because of course, if you have a stronger source, you're going to get more transitions. You're going to get more scattering, okay? So we're going to want to normalize this per unit flux, and its incident flux. So that incident flux, the incident flux of neutrons is, basically, it's basically the number of incident neutrons times their velocity. So it's going to depend on their velocity. So it's going to depend on the incident wave vector. The incident wave vector of the neutron is proportional to the incident velocity. So you get a factor that's kf over ki. That's where this factor comes in. Okay, these factors here are kinematic factors. Essentially, it's the mass of the neutron and then fundamental constants. Okay, and then you've got this matrix element, which we're going to have to worry about in a moment, and then this element of solid angle. So this element of solid angle is just telling us that, if the element of solid angle that I was talking about before with the scattering off my head up over here, if the solid angle that we're talking about is 2 degrees by 3 degrees, okay, then that will give us one answer. Okay, but if the solid angle that we're talking about is 5 degrees by 10 degrees, right, that'll give us a different answer. And that second different answer will be bigger than the first different answer. It has to be, because we're looking at a larger region of solid angle. Okay? So if you make the solid angle bigger, whatever your signal is, it'll go up. Okay? So we want to divide through by that. And so, so typically what we're interested in is this double, what's referred to as a double differential cross section. Okay? So it's d squared sigma d omega dEf. And so what this is it's how many neutrons are being scattered off the sample into a particular region of solid angle, okay, into a particular region of solid angle, and with a particular energy that lies, within some lower threshold of energy. So an energy that lies between EF and EF plus delta EF. Okay. So what fraction of neutrons are scattered to a particular solid angle with a particular energy? Okay? If we can understand that, we understand everything. Okay? And so we're going to write that down as this Kf over Ki and some factors that tell us how strong the scattering is, okay? But they don't otherwise tell us anything about the physics or the chemistry of the sample. And then everything else is going to go into this quantity called S of Q and omega. And S of Q and omega, that really does embody the physics and the chemistry of the sample that we're interested in. And so this is telling us that this experiment can be reduced to understanding, if you like, the intensity of neutrons that are scattered after transferring some momentum Q, which is going to be Ki minus Kf, and some energy h bar omega. Okay, so it everything kind of boils down to first-year physics, freshman physics kinematics, where you're doing an inelastic scattering experiment, and the only things that can happen are you're going to transfer some amount of momentum and some amount of energy to your sample, and basically you've got three things to do: conserve momentum, conserve energy, be logically consistent. If you do that, you're fine. Okay, and that's what we're going to do. Okay, so there's different types of information that you can get from this. In the same way that you can understand the structure of the material, you can understand the dynamics of a material. Even if the material itself is quite disordered. So you can imagine, for example, that there are two atoms that you're keeping track of in a particular collection of atoms. There's atom J prime, which initially is here, and there's atom J, which initially is over here. Okay, and then because of all the forces that are at work in the sample, this particular atom will move over here at some time t later. Okay, and so you could mathematically write down an expression that looks like this, which would let you understand that. It lets you understand that if there's an atom J prime at this position at time 0, what's the probability of finding another atom J at this position over here at time t? Okay, and that's expressible in terms of this pair correlation function. It's called a pair correlation function because it's telling you about the correlation between these pairs of atoms either at the same time or at different times. Okay, and that doesn't look very good, but it turns out we're not really going to use it. So basically, this S of Q and omega function that I was talking about before, it's basically giving you information about two Fourier transforms of this pair correlation function. It's a Fourier transform in space and then a Fourier transform in time. Okay, and this is just the same expression that I had before. It's this double differential cross section, Kf over Ki, the number of atoms, if you like, in your assembly times S of Q and omega, which is S of Q and omega. We could relate to this pair correlation function if that turned out to be a useful thing to do. Okay, so right, so that's what we're going to do. We're going to use inelastic neutron scattering to study the correlations, the pair correlations between how atoms move within a solid. So they'll move in a very specific way, which we'll discuss in just a moment. Okay, if we have a periodic crystal, and if we're looking at their normal modes of vibration, those are called phonons. You could have, if you had a molecular crystal, you could have vibrations of the molecules within the crystal, okay, which would tell you a lot about, basically how the molecule is put together, what the forces are that are at play. Those are referred to as librations or vibrations of the molecule within the molecular crystal. You don't need to have a crystal. You could have atoms which are diffusing, okay, within some sort of matrix, and you could get information about that. And you could have collective modes in materials which aren't periodic, okay? And so you might be interested in understanding these for general reasons, or you might want to understand the details of the interatomic potentials, because if you can understand the details of the energy versus momentum dispersion relations that describe, say, the phonons, then what you're really understanding is the nature of the interatomic forces that are at play in the solid, okay? So you can understand, the interatomic potential, which really means understanding the Hamiltonian of your sample at a very microscopic level, okay? So armed with that, actually, you can give that to your theory colleagues, and they can calculate everything, okay? So you can also look at phase transitions and how these normal modes would change as you go through phase transitions, and a variety of other types of topics of interest. So I'm not going to say very much about atomic diffusion, just because I think this is going to be covered in other lectures. But it's just that if you had a liquid or a disordered material, you can imagine that you might be interested in knowing, how a particular atom moves, okay, in the environment of all these other atoms, even though they're disordered. So here it is at time 0, and here it is at some later time t. It's diffused over here. And if this is conventional diffusion, then this can be, this distance over which it diffuses on average can be related to a diffusion constant, and it goes linearly with time. Okay, and this sort of information you can understand from what's referred to as quasi-elastic scattering. So we have scattering. And this has been known for a very long period of time. This is data from 1969. And so this type of motion, okay, we can relate it to what's referred to as a self-correlation function. So this is looking at the correlation between an atom at time 0 and the same atom at some later time t. Okay, and so you can write down this expression, at least in principle, for an autocorrelation function. Take 2 Fourier transforms of it, and you get the S of q and omega that's characteristic of this type of motion. Okay? And that actually gives you quasi-elastic scattering. So it's scattering that's centered on 0 energy transfer. Okay? And the thing to note here is that the scattering gets broader. So it gets broader in energy as you change the scattering angle or the momentum transfer. And so by measuring the energy width of this scattering, you can basically measure this diffusion constant. Okay. So you'll hear more about that sort of thing later. You'll hear more about this sort of thing later as well. So if you have a solid which is really better thought of as being made up of a collection of molecules, then the molecules themselves can have vibrations and librations and rotations and excitations that are kind of internal to the molecule. And those can be studied, and they can be quite complicated. So this is a spectrum taking from buckyballs, which are C60. Okay, and you've got all these different types of molecular vibrations and rotations and such. And if you intercalate a little bit of potassium into this C60, okay, and actually if you do this, it, amongst other things, it makes the material superconducting. So that's why people were interested in this at the time. And you change, by putting this potassium in here, you change a lot of these intramolecular excitations. So again, this sort of data can be used to understand the potential or basically the forces that bind together C60 to form the buckyball. Okay? And that you'll hear more about later as well. So we're going to be working a fair bit in momentum space or in reciprocal space. And the reason for that is because our scattering experiment, basically works in momentum space and energy space. So, the way we're going to think about the experiment is that, as I said before, the neutron comes in, it's going to transfer some amount of momentum, some amount of energy to your sample, and we're going to have to make sure, no matter what else we do, that we conserve momentum and conserve energy. Okay? So we're going to think of our crystal also in momentum space, and so physicists typically do this more than people from other disciplines. So again, if this is familiar to you or if it makes sense, great. If not, again, don't worry too much about it. But this description actually is very useful, particularly in materials which are periodic. Okay? So in crystalline materials, you have a particular arrangement of atoms. You might have, say, 10 atoms per unit cell. You might only have 1 atom per unit cell if you had an elemental solid. But you've got some arrangement of atoms in a unit cell, and then it simply repeats from one unit cell to the next. So once you understand where all the atoms are within a unit cell, okay, you're basically done, because then you know that all you have to do is repeat that structure from one unit cell to the next, and you've got the structure of the entire crystal. Okay, and the same way with regard to the phonons, which are telling you about how the atoms are moving about their equilibrium position. Again, once you understand the displacements, within one unit cell, again, you're pretty much done, and that's because of the periodicity of the crystal. And so this reciprocal space description of your crystal is basically, really comes into its own when your crystal is periodic. Because if your crystal is periodic with some lattice parameter that's given by A, so this is the distance between unit cells, or the repeat distance is A, then you can write down a reciprocal space representation of your crystal, which is itself a lattice. Okay, so this is itself a lattice, and you've got lattice points which are separated by 2 pi over A. So it's called reciprocal space because the unit cell dimension actually appears in the denominator here, so 2 pi over A. Okay, and then we're going to imagine, the rotations of our sample. So if we were to rotate our sample about some axis, the way we think about this is that we keep one point in reciprocal space fixed, and we rotate everything else about it. Okay, so this is how we're going to think about our crystal that has some unit cell parameter A, and this is how we're going to think about our crystal, and then we're going to superpose on that how we think about the scattering experiment. Okay, so this is how we think about the scattering experiment superposed on how we think about the crystal, and that is our experiment, right? It's the instrument, it's the incoming neutron and the outgoing neutron, and our crystal. That's the experiment. Okay, so the way we think about this is we've got an origin. So we've got our origin in reciprocal space. So this is the point that stays fixed. So if we rotate the crystal, we just rotate the reciprocal space underneath this. And we've set up our experiment such that we've got an incident neutron moving in this direction, so straight up, or not quite straight up, but up and to the right. So that's some incident wave vector ki. It has some definite magnitude. Okay, so this is a monoenergetic incident neutron, and then another monoenergetic scattered neutron. So here's kf and ki superposed on our crystal, and so the momentum transfer in the scattering event is ki minus kf. So it's this green vector here. That's the momentum transfer, and then the energy transfer in this case is 0 because the magnitude of ki is equal to the magnitude of kf. So this is elastic scattering that gives you a momentum transfer that is exactly equal to one of these reciprocal lattice vectors. Okay? And it turns out that this condition, that the momentum transfer of the scattering event is equal to any combination of reciprocal lattice vectors, that's another way of saying Bragg's law. Okay? So basically the way you think about this is that for this sort of scattering event, you imagine planes of the atoms in your crystal which have some real space separation A, okay, and you're Bragg reflecting a neutron with wave vector Ki into Kf, and you get constructive interference associated with the path difference from neutrons that reflect off one of these planes compared to the next one, and so forth. So this is the condition for elastic scattering. Okay? But you can see what we're really doing is I'm just taking a momentum space representation of our crystal, and I'm superposing on that a momentum space representation of the scattering experiment. So you put those two things together, and you can understand the scattering experiment. And so we're going to want to do that to understand these elementary excitations in solids, like, say, phonons. And what we're going to get out of this is we're going to be able to understand the energy versus momentum, okay, because that's what we do in a scattering experiment. We transfer some amount of energy and some amount of momentum to the sample, and we produce these elementary excitations. Okay? So now the thing is that the sample is usually not capable of accepting an arbitrary amount of energy or an arbitrary amount of momentum from the sample. It has to be a specific amount of energy and a specific amount of momentum. And that's because the only way the sample can accept energy from the neutron is if the neutron creates one of these elementary excitations, say one of these phonons. Okay? And the way to think about this, if you like, is that this is the way, this kind of might be the simplest way you might think about the forces that keep your atoms together in your solid. So why does any solid, like this solid, why does it hold together? And it holds together because you've got a collection of atoms, okay, with a positively charged nucleus. So here we've got 4 atoms. They're not all the same. You've got 2 big atoms and 2 small atoms, but they've all got nuclei that are positively charged. They've all got some electron cloud around them, which we're indicating with this sort of ring. And we're just going to put force constants between the nuclei and the electrons on different atoms and so forth. And we're going to do this the simplest way we can possibly do that. And so, again, freshman physics, what's the simplest way you can do this? Put a Hooke's law force constant between them, so you put springs between them, because we don't really have that much imagination. So that's what we're going to do. So we've got all these springs. Okay? And so you can kind of imagine, what would happen if you were to build out an infinite crystal like this, right? Well, so now everything is connected to everything else basically through these springs. Okay? And you can imagine that if a neutron, or even if you just came in and plucked one of these nuclei, okay, you just plucked one of these nuclei and brought it off of its equilibrium position, what would happen? Okay? Well, if these springs weren't here, you might imagine, or if you eliminated most of the springs, you might imagine that this one atom would go back and forth like this. Okay? But once you've got the electrons connected to the nuclei and such, if you take one of these atoms and set it into motion, everything will go into motion. Okay? And you'll have what are referred to as normal modes. And those normal modes will have a particular energy versus momentum relationship, which will depend in detail on these springs that we put in here. Okay? So if you can understand these energy versus momentum relationships, okay, if you can understand how the crystal absorbs energy from either a neutron or from its environment, you can understand what forces are at play between the atoms. Okay? And that's what we're really interested in. We're really interested in understanding microscopically what's going on in our samples. So that's what we're really trying to get at. Okay, so these phonons, we're going to imagine that the phonons are really displacements from the equilibrium position for the atoms, and it's for all the atoms in your solid. So for every atom, and they're going to be labeled with an index L, there's going to be some displacement for that atom at time t. It's going to go like 1 upon the square root of its mass, okay? And it goes inversely as the square root of the mass because It's like root k over m from harmonic oscillators and such. But it's basically just the larger the mass, okay, the smaller the acceleration for the same force. Okay, so higher mass objects tend to have frequencies that are relatively low. Okay, and we're going to have so there's going to be some polarization vector. That's this epsilon of j, and so that's telling you which direction the atoms are moving in and how big their oscillation is. Okay, so there's different types of oscillations. There's different types of normal modes that you can have. And if we simplify things down to a one-dimensional string of atoms, they're all the same now. We can imagine that we have these displacements of the atoms which are in the direction perpendicular to the wave vector of the phonon. So the wave vector of the phonon is in this direction, but the displacements of the atoms are up and down, right? So they're transverse. And so that's one polarization. Here's a different polarization where the displacements of the atoms are actually in the same direction as the wave vector. So this is a longitudinal mode. Actually, this would be a sound wave mode as well. So the sound waves that are reaching your ears from when I'm speaking are because there's compressional waves, there's density waves in the air, and that's what your ears are picking up. And you can see that you would get this is higher density than this, and so forth. Okay, so you get these different polarizations that correspond to different displacements of the atoms. Okay, and if you were to measure all of these in a real material like gold, which has this FCC structure, so it's a relatively simple material. There's only one atom per unit cell. Okay, but it's a three-dimensional crystal. So you have these relatively low-energy transverse modes. So the transverse modes are the other ones. Those are the ones where the displacements are up and down. And these relatively high-energy longitudinal modes, which are these ones here. Okay, so so can somebody tell me? So this is almost. So I'll tell you, it's almost always the case that the longitudinal phonons are higher energy than the transverse phonons. Okay, and so can somebody tell me why that's the case? Not Kyle. Sorry. Yeah. Well, yeah. So if you can put it in terms of the if you can think in terms of the Hooke's law springs, is there another way of saying that? I think you're basically right. It's about stretching springs, essentially. Sorry? Yeah, that's right. So here, so if you imagine that the atoms were all connected with springs. I think this is what you were saying as well. That here you're really directly compressing the springs. You're moving the atoms directly towards each other. So you're maximally compressing the springs and then maximally extending them. Whereas if you move them like this, you're kind of shearing the springs. Okay, so this is a lower energy mode than this is almost always. Okay, and so that's why this is a lower energy phonon than these are. Okay, but you can see anyway that it's relatively straightforward to map out all these phonons, and that's been done. And so the polarization, how do you tell polarizations apart? So for that, you need to understand in detail this S of Q and omega that I was talking about before. But for phonons, it's actually relatively straightforward. The piece that's really important is the piece that's circled here, is that the phonon cross-section goes like the dot product between the momentum transfer of the scattering event and the polarization vector of the phonon. So the polarization vector of the phonon tells you which direction are the atoms moving in and how far are they moving. That's basically what it's telling you. And it's that squared. Okay? So what this is telling you is that the phonon that you produce with the neutron, so if the neutron is coming in, it's giving a certain amount of momentum and energy to the sample. It's giving the right amount of momentum and energy to create a particular phonon. And the phonon it's going to create is one in which the the displacement of the atoms or the polarization vector of the phonon is parallel to the momentum transfer. So what that's really saying, because remember, the neutron's going to come in, it's going to interact with the nucleus, it's going to have a billiard ball type interaction, right? So it's going to go like this, right? And so if the neutron comes in and hits the nucleus and bounces straight back, okay, then the momentum transfer is all in that direction, right? So if it does this, so that means that the atom has to move in that direction, okay? Okay, it's, as I say, it's not very complicated. So what you can't have is this. You can't have this, and then the neutron goes like that. Okay, that doesn't conserve momentum, okay? So that's all that that term is telling you, right? It's not so complicated, in fact. Okay, so now the thing is that the wave vector of the phonon is really only defined to within the closest reciprocal lattice vector. So this little q in green that you see here is the wave vector of the phonon that we're talking about right now. And so that phonon wave vector is the same as this phonon wave vector. It's just relative to a different reciprocal lattice vector, okay? These black dots are the different reciprocal lattice vectors. But you can see that our scattering event would give us a momentum transfer q, okay? In this case, it's almost perpendicular. Big Q in red is almost perpendicular to little q in green. And this big Q in red, it's really going to produce displacements that are in this direction. So it's going to give us a transverse phonon. Whereas this big Q in red is parallel to little q, so it's going to give us this longitudinal phonon. Okay? So for the same wave vector q, in this example, for the same wave vector q, there are two phonons, right? So, the sample can absorb energy from the neutron at this wave vector only at this energy and at this energy and nowhere else. Okay? But when it does, it's going to produce, first this transverse phonon and then the longitudinal phonon. Okay? And this is what this data, this is the sort of thing that you'll see in this data. Okay. So that example that we did was the example where we have one atom per unit cell. Okay. But of course, pretty much everybody in this room is probably interested in materials where there's more than one atom per unit cell, because that's what modern material science is about. And if you've got more than one atom per unit cell, then other things can happen. Okay? And in particular, so the same thing can happen. Having more than one atom per unit cell, you can get the same sort of longitudinal phonons and transverse phonons that we had before. And in that case, it just means that if you've got two different types of atoms, you've got a heavy red atom and a light green atom, that they just basically oscillate together in phase. And the motion here is really the motion of an entire unit cell together. So an entire unit cell is moving in one direction, and then it moves back in the other direction. Okay, and so that's what you see here for these acoustic phonons. So these acoustic phonons are exactly the same as the acoustic phonons that we had in the case of lead, where there's only one atom per unit cell. Okay? But you can get other types of motion as well. You can get motion where the atoms within a unit cell actually beat against each other. They're out of phase with respect to each other. And that's referred to as this optic phonon here. Okay? So these have the same wave vector, or a very similar wave vector, but their eigenvectors are very different. Okay? So the acoustic phonons, the atoms within the unit cell are in phase. The optic phonons, the atoms that are within the unit cell, are out of phase. So as you complicate the structure, as you add more and more atoms per unit cell, okay, so here we have potassium bromide. You have these low energy acoustic phonons. These are these ones. And you have these high energy optic phonons. These are these ones. And the optic phonons, again, almost always higher energy than the acoustic phonons. And why? It's because, if you imagine there to be, Hooke's law type springs between the atoms, these are getting stretched a lot, okay? And these are hardly getting stretched at all, okay? So it makes sense. Okay, and so the more atoms per unit cell that you have, you always have the same number of acoustic phonons. Doesn't matter how many atoms per unit cell you have. Okay, they're all going up and down together in phase. So you always have, in 3 dimensions, you always have 3 acoustic phonons, but the more atoms that you have per unit cell, the more optic phonons you get. So there's actually 3 times n phonon modes in the crystal. Okay, 3 of them are always acoustic modes, so 3n minus 3 are optic modes, where n is the number of atoms per unit cell. Okay, so I think we're just about to get to the there it is, the evacuation. So I think we'll keep talking for a few minutes, and then we'll take our break when I think everything is calmed down. But this might be a good time to ask if people have questions over what we've done so far. Yes, please.
Do you ever end up in doing these kinds of measurements in situations where you have a problem where you're exciting multiple phonon modes at the same time?
Yes, yeah, very good question. Yeah, so everything that I'm going to tell you about, and in fact, most of the way we talk about these experiments, we assume that the neutron is coming in and exciting a single phonon. But you can get you can have multi-phonon scattering, so that the phonon can scatter twice in a given sample. And there's also processes in which the phonon can produce 2 excitations. So they're not necessarily 2 phonons, but they could be 2 phonons. So the key to all of this is just remembering that at the end of the day, you need to be conserving energy and momentum. So there has to be a mechanism to do that. But yes, you get multi-phonon processes as well. And actually, the cross-section for 1 phonon processes, you can see here, this is related to this cross-section, or the second double differential cross-section. It goes like q squared. It goes like the momentum transfer squared. So that's characteristic of single phonon scattering. If you had multiple phonon scattering, what you'd expect, or what you might kind of naively generalize, and it would be correct, is that the cross-section for multi-phonon scattering would go like q to the 4th or stronger, actually. Okay. But like I say, you've got to figure out a way that you can conserve energy and momentum. And if I just go to this diagram here, you can see that, for example, if I set up my scattering experiment such that I was sitting at this point in momentum and energy transfer, the neutron cannot inelastically scatter there. Okay? It can only scatter when it gets to here, and then again when it gets to here. So for multi-phonon scattering, you'd have to figure out, again, how you would do that and conserve momentum. But multiple scattering is an issue. I mean, one of the things that we do in experiments is we typically measure what fraction of the neutrons go through the sample without interacting at all. And you kind of want that to be at around the 70–80% level. You want there to be some scattering, but you don't want there to be so much scattering that the chances are that a given neutron is scattering more than once in the sample, because it's not that it's impossible to include that in your analysis, but it's more difficult. Other questions? Okay. So I'm just going to see where we are here. Oh yeah, so just to complete that argument. So, if this is what you get for 2 atoms per unit cell, right? This is what you get for something more like, I'm going to say about 14 atoms per unit cell. Okay. So the more atoms per unit cell that you have, the more phonon modes that you have. Okay. And it can quickly get quite complicated. But you can see that the low energy phonons are always the same. The low energy phonons are always the same and are always relatively easy to understand. Okay. So the next thing that I would have done would have been magnetic excitations, but I'm actually not going to do that now because I'm going to do that in a separate lecture in about an hour. So Jaime, do you know how long it's going to take before we can take our break? Yeah. Okay. So maybe we'll go for another 10 minutes and then take a break, and people can use the washroom and get coffee and such. Yeah. So, yeah. So it's up to you. Would you like a short break now, or do you want me to keep going for a little while, and then you can have a break where you can use the washroom? And that sounds more sensible, right? So okay. Okay, so then I'm going to change directions a little bit and talk about neutron instrumentation. So I'm going to be talking about things that are more practical for essentially the next hour or so. And so this is actually a layout of a triple axis neutron instrument. So this is the instrument that Burt Brockhaus invented in the 1950s and 1960s. And in retrospect, actually, it's a very simple instrument. So what this instrument lets you do is it lets you do exactly what I said earlier. It lets you systematically conserve energy, conserve momentum, be logically consistent. That's it. Okay. And so, in fact, it's so simple now that I kind of it's hard to put yourself back into the time period when these things were being developed. But actually, it wasn't appreciated as a simple instrument originally. It was thought to be quite complicated. But as I'll show you, it really isn't. So this is the layout of the instrument. And the way this instrument works, and the way a lot of neutron instrument work, is that you determine the neutron energy and the neutron wave vector, velocity, and such by measuring the neutron's wavelength. Okay? And you do that with two monochromator crystals. So there's a crystal here, there's another crystal here. And they both are using just Bragg's law. So n lambda equals 2d sine theta. And so we've set things up so that for a particular angle of incidence and angle of reflection, okay, from the atoms in this crystal here, that we get constructive interference for a particular wavelength going in this direction. So this crystal, if you have a white beam coming into the monochromator, you'll have basically a monochromatic beam going out in this particular direction. That's selected by Bragg's law. So this monochromatic beam of neutrons will go towards a sample. Here's our sample. And these neutrons, of course, will scatter off the sample in all directions. And our job, as usual, is to determine the relative number of neutrons that have scattered off in all these different directions. And we're going to do that one direction at a time. So we're going to start with this direction over here. We're going to measure the relative number of neutrons that have scattered off the sample and are going in this direction. And then we perform another energy analysis or another wavelength analysis of this beam going in this direction, because only the neutrons which, again, satisfy Bragg's law for this crystal will scatter off into our detector over here. Okay? So that's basically how the experiment works. I said before that we start with a white beam of neutrons, but actually we start with whatever the source back here gives us. Okay? So the source back here is a reactor, and the reactor will have some flux of neutrons as a function of energy, if you like. I've written it here as a flux as a function of velocity, but it could be energy as well. And depending on what we're looking at, so if we have the reactor core sitting in water at room temperature, then the flux of neutrons that we'll see will be this flux in black, okay, that's labeled 300 Kelvin, because this is a Maxwellian distribution, centered on the energy of 300 Kelvin, which is 25 millielectron volts. Okay, so most of the neutrons are at 25 millielectron volts. There are some that go up to quite high energies, and there's some that go down to low energies. But if instead of looking at the water surrounding the core of the reactor, if we looked at a bucket of liquid hydrogen surrounding the core, which is referred to as a cold source, okay, then those neutrons would then come into equilibrium not at 300 Kelvin, but at 20 Kelvin. Okay? So the Maxwellian distribution, you get the same Maxwellian distribution, but it'll be pushed down to lower temperatures, to lower energies. Okay, so this is what you would get if you're looking at a cold source, and this is what you would get if you're looking at a so-called hot source. So a hot source is typically a block of graphite, and it just gets very hot. If you put it in a reactor, it goes up to 3,000 Kelvin, and it doesn't melt or burn. That's certainly what you hope. And so then the neutrons come into equilibrium with it, and you get this distribution at higher energies. Okay, so that's basically the outlay of the instrument. And now this first monochromator crystal that you get over here, okay, it's going to pick out. I was saying that it's going to pick out a particular energy, that it's going to get a monochromatic beam. But of course, you never get a monochromatic beam, and you don't want a monochromatic beam. Okay, what you're going to get is you're going to get a low energy cutoff and a high energy cutoff. And that's going to be determined by this Bragg diffraction condition. Okay? So you're not actually going to get lambda neutrons. You're going to get lambda plus or minus delta lambda. And so that's going to give you this range of neutron wavelengths or neutron energies between the dashed lines that you see here. Okay? And it's very important that you get a range, because the incident flux of neutrons that you're going to be giving to your sample is going to be proportional to the area underneath this curve. Okay? And so if you bring those two dashed lines together, you're going to have no area between your curve, and you're going to have no incident intensity. Okay? So this is one example of a very general situation, which is that your resolution and your intensity are inversely related, and you typically trade them off. So if you feel that your experiment doesn't have enough intensity, you relax your resolution. If you want more resolution because there's some piece of science that you're looking for that you can't quite see in your data, it's going to cost you intensity to get it. Okay? And so you can see that as you bring these two dashed lines together, you're better and better defining the incident energy, the incident wavelength, but you're doing that at the cost of intensity. So intensity and resolution actually often trade off, and they will here. Okay? So what this experiment, or what this apparatus is doing, it's giving you a mechanism to select a particular wave vector for the incident neutron going towards your sample. That's with this monochromator. And it's giving you a particular scattered neutron wave vector with this monochromator crystal here. Okay? So you're determining this incident wave vector and this scattered wave vector. That's what you're determining. Okay? And you simply subtract these two off, so it's Ki minus Kf. So this is the momentum transfer of this scattering event. That's the momentum transfer, and this is the energy transfer. So the neutron, so this particular event is scattering this amount of momentum and whatever this amount of energy is. Okay, and if it's drawn the way I drew it here, Ki, the magnitude of Ki is approximately the magnitude of Kf. So this would be elastic scattering, but it doesn't have to be that way. Okay. So you also often see a variant of the triple axis experiment, which might even be performed on a triple axis instrument. Triple axis instrument is very versatile. In fact, that's one of its great strengths, right? It's actually made up of a whole bunch of components, and you can switch them in and out to suit the science that you're doing. So there's a lot of different types of measurements you can do. So one of the things that is often done, and it might be done by design. So for example, HB1A is no, actually HB1A is a triple axis with just fixed tooth 8M. Sorry about that. So not a good example. So we could have a triple axis instrument where you remove the second monochromator. So if you only have one monochromator here, then what you're doing is you're defining the incident wave vector, okay, by using the first monochromator. So that's defined. Ki is defined. And Kf, the direction of Kf is defined, but you remove the second monochromator here. Okay? So you're not doing any energy analysis of the scattered beam. You're only taking out those neutrons which are moving in this direction. Okay? So what you're getting simultaneously is you're getting this Ki, but all of these Kfs. You're getting them all at once. And it might be that elastic scattering is much stronger than the inelastic scattering. So red to red is elastic scattering. Red to purple or red to green is inelastic scattering, because Kf does not have the same magnitude as Ki, right? So it could be that there's so much more elastic scattering than there is inelastic scattering that you can't tell the difference, and this all looks like inelastic scattering. But it's important to remember that if you're not doing an energy analysis of any of your beams, then all those energies are in principle in your beam, and how much you get is just dependent on the inelastic processes that are going on in your sample. Okay. But this type of measurement, which is sometimes referred to as a two-axis measurement, is often employed as well. And sometimes people just refer to it as elastic scattering and as diffraction. But if you're not doing energy analysis, then you definitely have inelastic scattering in your beam. Okay. So that is, okay. Oh. Okay. Well, that might be the end of. Okay. So anyway, there's other pieces in here. You can see this is a schematic of the instrument. So we've gone through the monochrometers, but there's also these things called solar slits in between here. So the solar slits are basically devices, and they're modular devices, so you can put these in, you can take them out. And what they are, they're boxes that are made up of sheets of metal. Everything's clear? Yeah, okay. So we'll just finish this, and we'll take a break. So they're boxes that are made up of sheets of metal, and the sheets of metal are either themselves absorbing, or they're coated with a paint which is absorbing. They absorb neutrons. So what they do, so these are parallel sheets of metal. I don't know how well you can see them, but you can probably see them better here. And what they do is that they ensure that the neutrons going from the monochrometer to the sample and from the sample to the second monochrometer, that they define the direction of those neutrons better and better. And so these are also used to improve your resolution or to define your resolution. Because the tighter the collimation, so the more slits that you have, okay, the higher the tolerance is on the direction of the neutron. Okay, so if the neutron will only make it through from the monochrometer crystal to the sample if it doesn't touch the sides of the solar slits, the sides of the sheets of metal here. Because if the neutron does touch the sides of the sheets of metal, it'll get absorbed. Okay? So you make your resolution better by putting in more of these slits, by better defining the direction the neutron has to go from, say, the monochrometer to the sample. And you make your resolution worse by removing those slits and making, if you like, making the distance between the slits farther apart. Okay? And again, this really indicates that you improve resolution by giving up intensity, and you loosen your resolution, you will increase your intensity. Because here, where are your neutrons going when you tighten your resolution, when you tighten this angular dependence? They're getting absorbed. They're being removed from the experiment. So again, there's this inverse relationship between intensity and resolution. Okay, so I think we'll break for, say, 10 minutes or 15 minutes. So we'll reconvene at 10 o'clock then, okay?